Welcome to this comprehensive walkthrough of IGCSE Physics focusing on thermal properties and temperature. In this video, we'll explore key concepts, solve typical exam questions, and clarify common misconceptions. Whether you're preparing for your exams or just looking to strengthen your understanding, this session will guide you through the essentials of thermal physics, including specific heat capacity, latent heat, thermal expansion, and thermometer calibration. Let's begin by setting the stage for what thermal physics is all about and why it's crucial in understanding the physical world around us. Let's start with a practical question involving specific heat capacity. Imagine a beaker containing 0.5 kg of water at 30 degrees C. The water is heated, and its internal energy increases by 21 kJ given that the specific heat capacity of water is 4200 J/kg degrees C. We're asked to find the final temperature of the water. This type of calculation is common in exams and helps you understand how energy input relates to temperature change. We'll break down the formula, substitute the values, and solve step by step, reinforcing the importance of units and methodical problem solving. Next, let's interpret a temperature time graph for a substance losing heat at a steady rate. The graph shows a segment labeled PQ. Understanding what this portion represents is crucial for recognizing phase changes and energy transfers. We'll discuss how a flat segment on such a graph typically indicates a phase change, where temperature remains constant as energy is used to change state rather than increase temperature. This scene will help you identify whether the substance is condensing, cooling, or solidifying based on the graph's features. Thermometers are calibrated using fixed points, typically the melting point of ice and the boiling point of water. In this scenario, a student has 4 beakers: P with ice and salt, Q with ice and water, R with boiling salt solution, and S with boiling water. Which beakers should be used to check the fixed points? We'll clarify the concept of fixed points, why pure substances are used, and how impurities affect boiling and melting points. This is a foundational concept for understanding temperature measurement accuracy. When ice at 0 degrees C starts to melt, what happens to the energy and temperature? This question tests your understanding of latent heat. As ice melts, energy is absorbed but the temperature remains constant until all the ice has turned to water. We'll discuss the concept of latent heat of fusion and why temperature doesn't rise during the phase change, even though energy is being supplied. This principle is key in many natural and industrial processes. Let's solve a classic energy transfer problem. If 5g of water at 25 degrees C is dropped onto a large block of ice at 0 degrees C, the water cools to 0 degrees C and some ice melts. Assuming all energy lost by water is gained by the ice, how much ice melts? We'll use the specific heat capacity of water and the specific latent heat of fusion of ice to set up and solve the energy balance equation. This example reinforces the importance of energy conservation in thermal processes. Thermometer sensitivity is crucial for accurate temperature readings. The diagram of a liquid in glass thermometer prompts us to consider how design affects sensitivity. We'll discuss why increasing the internal volume of the bulb and the volume of the liquid enhances sensitivity, while other modifications like increasing the tube's diameter or glass thickness have different effects. Understanding these design principles helps explain why thermometers are built the way they are. When measuring specific heat capacity in an experiment, it's important to use the correct formula. If a block of aluminium is heated and its temperature rise is measured, with energy input E mass m and temperature change delta, which expression gives the specific heat capacity, we'll clarify the formula C equals E/m delta. Explain each term and highlight common mistakes students make when rearranging or substituting values. Thermal expansion varies across the 3 states of matter. Which state expands the most when heated? We'll compare solids, liquids, and gases, explaining that gases expand the most, followed by liquids, then solids. This concept is fundamental in understanding why bridges have expansion joints and why hot air balloons rise. We'll also touch on practical implications in engineering and daily life. Let's revisit thermometer design, focusing on which features affect sensitivity. Is it the mass of the liquid, the diameter of the thread, the length of the stem, or the thickness of the glass bulb? We'll break down how each feature influences sensitivity, helping you remember which design choices matter most for accurate and responsive temperature readings. Suppose you want to measure the specific heat capacity of copper using a block and an electrical heater. You already know the power of the heater. What other apparatus do you need? We'll discuss the importance of a thermometer to measure temperature change and a balance to measure mass. This scene emphasizes the practical setup for a classic physics experiment. 0.2 kg substance is heated at a steady rate of 500 W, and its temperature time graph is provided. How do you calculate the specific latent heat of fusion? We'll walk through the process. Identify the time interval during which the substance melts, calculate the energy supplied during this interval, and divide by the mass to find the latent heat. This method is widely applicable in both exams and laboratory settings. To calibrate a thermometer, where should the bulb be placed to mark 0 degrees C? The answer is in pure melting ice. We'll explain why using pure substances ensures accuracy and how this process is fundamental to thermometer calibration. Understanding this helps avoid errors in temperature measurement and is a key point in practical physics. Given a temperature time graph for a solid being heated, how do you identify when it has just become completely liquid? We'll discuss the features of the graph, focusing on the end of the flat segment where temperature starts to rise again. This point marks the completion of melting, a critical skill for interpreting experimental data. Two metal blocks, X and Y, are heated by 10 degrees C. Block Y has a greater thermal capacity than X, which block needs more energy to heat up, and which loses more energy when cooling. We'll explain that higher thermal capacity means more energy is required for the same temperature change, and more energy is released when cooling. This concept is vital for understanding heat storage and transfer in materials. On a heating curve for a solid between which points is the substance partly solid and partly liquid, we'll analyze the graph, focusing on the segment where temperature remains constant, indicating a mixture of phases. Recognizing this is essential for interpreting experimental results and understanding the energy involved in phase changes. When a circular metal disk is heated, which property decreases? The answer is density. We'll explain that as the disk expands, its volume increases while mass remains constant, leading to a decrease in density. This principle is important in material science and engineering applications. If the same amount of heat energy is given to two objects, X and Y, but X's temperature rises less, what does this tell us? It means X has a larger thermal capacity. We'll discuss how thermal capacity affects temperature change and why materials with high thermal capacity are used for heat storage. A block of copper and a block of lead are heated with the same energy input. Copper has a lower thermal capacity than lead. Which block's temperature increases more? We'll explain that the block with lower thermal capacity, copper, will experience a greater temperature rise, reinforcing the relationship between energy input, mass, and specific heat capacity. A mercury in glass thermometer is calibrated by measuring the length of the mercury column at 0 degrees C and 100 degrees C. If the length at 0 degrees C is 2 cm and at 100 degrees C is 26 cm, what is the length at 50 degrees C? We'll demonstrate how to use proportional reasoning to interpolate between fixed points, a useful skill for both exams and laboratory work. Before moving further, let's clarify some key definitions: specific heat capacity, latent heat, thermal capacity, and thermal expansion. Understanding these terms is essential for tackling both theoretical and practical questions in thermal physics. We'll provide concise definitions and examples for each, setting a solid foundation for the rest of the video. Let's discuss the energy transfers involved in melting and freezing. When a substance melts, it absorbs energy without a temperature rise. When it freezes, it releases energy, again with no temperature change. This is due to the latent heat of fusion. We'll illustrate this with real-life examples and connect it to the earlier questions on phase changes. In a typical lab experiment to measure specific heat capacity, you'll need a block of the material, a heater, a thermometer, and a balance. We'll walk through the steps: measure the mass, record the initial temperature, supply energy, record the final temperature, and calculate using the formula. This practical approach reinforces theoretical understanding and prepares you for lab assessments. Thermal expansion isn't just a theoretical concept, it has real-world consequences. We'll look at examples like railway tracks, bridges, and thermometers, explaining how expansion joints and design considerations prevent damage. Understanding these applications helps you appreciate the importance of thermal physics in engineering and daily life. Let's compare the latent heat of fusion, melting, and vaporization, boiling. Both involve energy transfer without temperature change, but the amounts differ significantly. We'll discuss why vaporization requires more energy and how this affects processes like boiling water and sweating. Energy conservation is a core principle in thermal physics. Whether heating, cooling, melting, or freezing, the total energy in a closed system remains constant. We'll illustrate this with examples from earlier questions, emphasizing the importance of careful energy accounting in calculations. Different materials conduct heat at different rates. Metals are generally good conductors, while insulators like wood and plastic are poor conductors. We'll discuss how this affects temperature changes and why material choice is important in thermal applications. Calibrating a thermometer involves marking fixed points using pure melting ice and boiling water. We'll outline the step-by-step process, explain why accuracy matters, and discuss common sources of error. This practical knowledge is essential for lab work and exam questions. While the Celsius scale is common, other temperature scales like Kelvin and Fahrenheit are also used. We'll briefly compare these scales, explain their fixed points, and show how to convert between them. This knowledge is useful for interpreting scientific data and exam questions. Thermal equilibrium occurs when two objects in contact reach the same temperature and no net heat flows between them. We'll discuss how this principle underpins many thermal processes, from mixing liquids to designing heat exchangers. It's important to distinguish between heat and temperature. Heat is a form of energy transferred due to temperature difference, while temperature measures the average kinetic energy of particles. We'll clarify these concepts with examples and analogies to prevent common misunderstandings. Latent heat plays a role in many everyday phenomena, from ice melting in a drink to sweating during exercise. We'll explore these examples, connecting theory to real-world experiences and reinforcing the practical importance of thermal physics. Thermal expansion can cause problems like cracked pavements or jammed doors, but it's also harnessed in devices like thermostats and thermometers. We'll discuss both the challenges and benefits of thermal expansion, highlighting the need for careful design in engineering. Heat can be transferred by conduction, convection, or radiation. We'll briefly explain each method, give examples, and discuss their relevance in thermal physics. Understanding these mechanisms is essential for explaining how heat moves in different situations. Thermal insulation is used to reduce unwanted heat transfer. We'll discuss materials and methods for insulation, from double glazing to vacuum flasks, and explain the science behind their effectiveness. This knowledge is useful for both exams and everyday problem solving. To measure latent heat in the lab, you need to supply energy to a substance as it changes state and measure the mass and energy input. We'll outline the procedure, discuss sources of error, and show how to calculate latent heat from experimental data. Thermal properties of water and air play a major role in climate and weather patterns. We'll discuss how specific heat capacity and latent heat affect temperature changes in oceans and the atmosphere, influencing weather events and climate stability. Success in thermal physics questions requires careful reading, clear understanding of concepts, and accurate calculations. We'll share tips for approaching multiple choice and calculation questions, managing units, and avoiding common pitfalls. These strategies will help you maximize your marks on exam day. Students often make mistakes with units, formula rearrangement, or misinterpreting graphs. We'll highlight these common errors, show how to avoid them, and reinforce best practices for accurate and confident problem solving in thermal physics. Let's summarize the key points from this session. Understand and apply the concepts of specific heat capacity, latent heat, thermal capacity, and thermal expansion. Practice interpreting graphs, calibrating thermometers, and solving calculation problems. These skills are essential for mastering thermal physics at the IGCSE level. For more practice and in-depth explanations, check out reputable educational websites, textbooks, and past exam papers. Consistent practice and review are the best ways to reinforce your understanding and improve your performance in thermal physics. Thermal physics connects to other areas of physics, such as energy, forces, and electricity. Understanding these links helps you see the bigger picture and apply your knowledge across different topics in the curriculum. Thermal physics is not just academic, it's used in engineering, meteorology, environmental science, and more. We'll highlight some careers where understanding thermal properties is essential, inspiring you to see the value of what you're learning. Let's quickly review the practice questions covered in this video. We'll recap the main ideas, correct answers, and reasoning behind each, reinforcing your understanding and helping you identify areas for further study. Congratulations on making it through this comprehensive review of thermal properties and temperature. Remember, mastering these concepts takes time and practice. Stay curious, keep practicing, and you'll build a strong foundation for success in physics and beyond.